Welcome to Aphonic. We've designed a pair of active noise-canceling headphones that allow the user to tune their listening experience to their environment. Noise-canceling headphones today use destructive interference to cancel unwanted noise, meaning if a dog is barking outside, or if you hear a tone that you wouldn't like to hear, your headphones will immediately detect and inject an opposite signal that destructively interferes inside your ear and ensures you hear absolutely nothing. So in industry, people use a mix of feed-forward and feedback techniques to ensure maximal performance across a wide band of frequencies. What this means in practice is there's typically a mic on the inside of the ear cup as well as on the outside of the ear cup that listens to what the user is hearing at the moment, as well as the sound that is heard outside, and balances these two to ensure that the user hears absolutely nothing. So headphones today are pre-configured with these settings and largely create an all or nothing process where the user hears nothing or everything when they take off their headphones. ANC does a great job of isolating you from your environment in this way, but a poor job of integrating you with it. And this is the gap that we want to bridge. Users should be able to adjust their listening experience to their environment by picking sounds from their ambient environment that they'd like to listen to while listening to their music. So our solution is to use AI to give the user some degree of flexibility to listen to the sounds that they'd like to hear. Typically, this is a very computation-heavy process using typical DSP techniques, since you'd have to have large amounts of memory to understand this is what a dog sounds like, this is what a helicopter sounds like, this is what rain sounds like. I've included some spectrograms on the right just to give a very brief look into how much data needs to be allocated for each individual sound that you would need to process in real time, which makes this an extremely difficult process to kind of go through. So our goal is to use a machine learning based approach that can bridge this gap without extremely large memory requirements. So our headphone build included 5 main parts. There's a rear ear cup, which we'll explain in a second, a PCB, which routes signals from the internal and external mics down to a separate off-board computing board, an acoustic chamber that is used for isolating high frequencies from entering your ears, a headband and a hinge to integrate the headphones together, as well as a front ear cup and a coupler that will give some space for our speaker driver to sit, as well as our internal mic to rest, as well as the ear pads to mount onto the headphones. So we can start with the headband. Our headphone headband is engineered around an average human head shape to maximize ergonomic comfort and durability. It's made from a flexible, durable resin, provides long-lasting comfort and resistance to wear. An adjustable mechanism ensures precise fitting across diverse head sizes, enhancing user experience over prolonged usage periods. As you can see, we have a graphic of our headband shown in this slide. Next, we have the ear cup and coupler. The ear cup and coupler design draw inspiration from industry benchmarks like the Bose Quiet Comfort and Sony XM series, renowned for incredible noise isolation and ergonomic comfort. The ear cup serves as the primary housing for internal electronics as well. It's carefully designed to balance spatial efficiency with functional performance, ensuring both compactness and acoustic integrity. Here we have the acoustic chamber. The acoustic chamber, based on analysis from the Sony XB design, provides an isolated volume of air between the headphone driver and the user's ear, crucial for tuning the headphone acoustic response and distortion characteristics. The design of this chamber allows for approximately 50 centimeters cubed of controlled airspace, allowing the headphone driver to breathe effectively, resulting in improved bass response. Aphonic incorporates high-performance 50mm 32-ohm dynamic drivers paired with two 6mm electrode microphones. The chamber design ensures proper driver performance by maximizing air availability while minimizing external acoustic interference. The PCB functions as the central hub for electrical connectivity, managing power distribution and signal routing between internal components such as drivers and microphones. Its compact design is specifically optimized to occupy minimal volume, strategically positioned near the rear of the acoustic chamber to preserve acoustic performance and internal spatial constraints. So now let's talk about the integration of machine learning. By record, processing, and re-injecting our signal using a machine learning interface that we're running on a separate computer, we're able to identify sounds from the soundscape without excessive amounts of memory to keep track of every single spectrogram possible. And we're able to classify those sounds, resynthesize them, and then re-inject them into the user's ear in a very streamed format. So short bursts of 10 milliseconds are injected into the machine learning model. The decoder, guided by a user-defined preference, generates an adaptive filtering mask around the incoming sound. And then the mask isolates the desired sounds from ambient noise and reconstructs the filtered audio output. Our digital signal processing is architected such that we can achieve active noise canceling over a wide band of frequencies. We use a combination of feedback and feed-forward techniques, just like what's used in industry, in order to achieve high-fidelity real-time noise canceling within 22 microseconds. We use external mic data and pass it through some custom-designed filters, as well as internal mic data, which is passed through two adaptive filters in order to create our cancellation signal. In addition to this, music and selective pass-through signals that are generated by our machine learning model are injected into the audio stream, such that the user can concurrently listen to sounds from their ambient environment, listen to music, and experience noise canceling in the way that we've architected it. Thank you.